Let's recap Chapter 5. This is a big deal. You learned a whole new mathematical operation, and you did a lot with it all in one chapter. First, just as big a picture as we can get here. Remember that, for a derivative, what we were finding was the slope of the line at any given point. For an integral, what we're finding is the area underneath the function. And the first way that you learned how to do that was by a geometric formula. So that's if you draw your picture and you're finding the area under the curve using some geometric formula, usually a rectangle, a triangle, trapezoid, or a circle. That's the one I wanted to remind you about, is if you have something that looks like, say like that. Remember that this right here is r squared, and so that's telling you you've got a circle here with a radius of 3. Half circle, we've only got the top half of that square root. If you get stuck, go ahead and graph it. I just don't want you wasting your time in the calculator graphing things that you don't have to. But if you get stuck, you have my blessing. Go graph it and take a look at it. And so then you do have to remember there that your area is pi r squared. Don't forget that areas above the x-axis are positive. Areas below the x-axis are negative. That does matter. We got more sophisticated when we started doing Riemann sums and the trapezoid rule. And so remember, with a Riemann sum, you have 3 options. You can do a left endpoint, a midpoint, or a right endpoint rectangle. And it matters. So let's say I have to do a left endpoint rectangle. That means that the left side of my that was a terrible straight line. The left side of the rectangle touches the function. The left side touches the function. Left side. So let's say I want to evaluate this integral with 4 left endpoint rectangles. The reason I want to stress this to you is you have to follow the directions. Let's say you know this function. The problem has to give you that function so that you can, find those y coordinates. And you may be tempted to say, well, I know how to do this. I can just integrate it. I can do the fundamental theorem of calculus and just find the answer. And I want to caution you that the answer choices are going to be really close together on these numerical integration problems. And the exact answer, the one you would get by doing it, by hand, is going to be an answer choice. And it will be wrong because the directions will have told you to use a left point. And I guarantee you that if you use midpoint, that answer choice will be there. Right endpoint, that answer choice will be there. You have to follow the directions and carry out lots of decimals. Don't round until you get to the very end. Because this does, in this particular case, this overestimates the area, right? We've got this extra space here that overestimates that area. So this will not match the exact integral if you can do that by hand. And then, of course, there was the trapezoid rule. And don't forget, if you're looking at the area of a trapezoid, you've got area is 1/2 base 1 plus base 2 times the height. It is repetitive and it's tedious, but it gives pretty good results. And there are some functions that you just cannot integrate using an antiderivative, and you have to use one of these numerical techniques. So speaking of those antiderivatives, this is when you start doing the integrals exactly, algebraically. We've always got the power rule, right? If I want to integrate x cubed, you add 1 and divide by it. So your integral is x4 over 4. And if you're doing just the antiderivative, you're not doing a definite integral, don't forget your plus c. Some of our special cases, if we can't do it by the power rule, your trig functions, you just have to work backwards from the derivative. There's no good way around it. You just have to go backwards from the derivative. Don't forget that the integral of e to the x is just e to the x. And don't forget that 1 over x, the integral of that, gives you natural log of x. I don't think we talked about integrating the actual natural log of x. There's a formula for that. It's x natural log of x plus x, no, minus x plus c. Anyway, there shouldn't be any of those on the test. I don't know why I went there. I'm sorry, I'm back on track. After indefinite integrals and antiderivatives, we talked about the fundamental theorem of calculus, and that's when you have limits of integration, right? And these are easy. You integrate f of x, and then you evaluate it from a to b. The only way you can mess that up is doing it out of order, so just remember that it's the upper limit minus the lower limit. You've got lots of practice doing those. Then we did U substitution. This is where you really expand the the number of problems that you can do. And the key with U substitution is it's just like the chain rule. You're looking for a function inside a function. If you have e raised to the cosine of x, if it's not just plain old e to the x, that's my red flag that, hey, I should let that be equal to u. And then remember what you do is you take the derivative and we follow the chain rule. So I've got that dx on there. I should probably finish writing the problem if I'm going to do an example here. Back down here, solve this for dx. And then you plug everything in. You're going to replace this with u, and then replace your dx with whatever you solved for here. Go ahead and integrate. If it's an indefinite integral, then you'll sub everything back in, put it in terms of x. If it's a definite integral, if you've got numbers here, change your limits of integration. Promise you, it is always easier to use your definition of u to change your limits of integration. So you plug a in, get that number, plug b in, get that number, and use those for your new limits in terms of u. And it's going to be so much easier to evaluate. It always is. And then last thing we talked about were the physics equations. And the big picture there was if you have acceleration, you can integrate to get to velocity. You can integrate that to get to position. If you want to go backwards, you can go from position to velocity by taking the derivative. Go from velocity to acceleration by taking the derivative. So we integrate in this direction, take the derivative in this direction. The big thing though is when you are integrating, you have that plus c term, and you find out c, the word problem has to give you some more information. It's got to give you a data point. If it says, the object was initially at rest, that tells you that when t equals 0, v of t is also equal to 0. The initial height was 45. I think we just saw that problem. It tells you the position at t equals 0 is 45. So just keep that in mind. You can't just ignore the c. You've got to use a data point to solve for it. And then the other big thing there, and hopefully you remembered this from physics, if you have a velocity versus time graph, the integral of that graph gives you the displacement. If your graph goes positive and negative, the integral still gives you the displacement, but it doesn't tell you how far the object actually traveled. If you want to know the distance the object traveled, you have to add the absolute value of those integrals together. So what that means for us algebraically here is to get the displacement, you just have to integrate v of t. But to get the distance traveled, to get the total distance traveled, you have to integrate the absolute value of the velocity. We don't have a good algebraic way to do that, and so what we have to do is we have to see where the object changes direction. Remember, that happens when v of t equals 0. Any candidates that we get for t, we should plug those into a of t and make sure that a of t is not equal to 0. If a of t equals 0, then you don't have to mess with that time. Once you find any times where the object changes direction, then you break up your integrals. So you'll integrate from whatever your lower limit was to that time that you just found, plus the integral of that time you just found to your upper limit, whatever that happens to be. You'll get those answers, take the absolute value of them, and add them together. That gives you that total distance. Okay, big test. This is important stuff.